Okay, so I count on you to let me know when it's time for lunch. I'm going to show you a function. I'm going to demonstrate it so we can move on to the next chapter where things become even more interesting. So for example, we have this, the variable x here that contains, so it's a vector of characters. So R has no knowledge that the fact that the first and the third one are the same. Not that it's relevant for what I want to do now. But, so it's not a factor, x. And there's the function unique that will return the unique elements of that vector. And so we can apply this, for example, IPRG $condition. Okay, so if we type IPRG $condition, we extract that specific column from the data frame, and we get, what is it, 36,321 values. But that's not really informative at this stage. We want to know how many conditions we have. And so here we could use unique to show us the unique values that we have in this condition column. And now it's easy enough to look at them and see that we have condition of 4 conditions. But if we want to know, well, how many proteins do we have that were quantified in this experiment? If we say unique IPRG proteins, we have too many to look to find out. So we could now combine length and unique to get, and now we run this. So I asked to first, of all the proteins, all the values for that variable proteins, to only keep the unique ones, but there are still too many to kind of look at. And so now I feed this into length to find out that I have 3,027 unique proteins that have been quantified. And they have been quantified over, for different conditions, different replicates, and so on. Yes?
So, okay, so if there was like one in A in there or 1 0, would that count as a unique?
Let's try. Let's try. So I'm going to make something up here. A, B, and I'm going to add an A. I'm going to call this X. Oops. And so unique X, well, I expect to see A, B, and then let's see what the effect of an A is. And so it says my unique observations are A, B, and missing values. So let's try if I have multiple missing values. It's still A, B, and A. So it tells me that among my unique missing values I have, my unique elements I have missing values. Now, is there an A.rm? I don't know. We can look it up. Question mark unique. No, there is no A.rm in this case. So there is no inbuilt way in unique to say remove first missing values. We would have to do that manually. Okay, so we're going to learn slightly new technique. Oh, yes, sorry.
So just another question about the NA.
Yes.
So say you have an empty cell in a column with numbers.
Yes.
Does that mean I interpret the entire column as characters now?
That's a very good question. There are actually different types of NAs.
Okay.
There are NAs saying that this is a missing number, and there are NAs that say this is a missing character. And so R will not look at the missing values to infer whether that column, that variable, should be a number or a character. It will look at all the non-missing values. And if all these are numbers, at the end we will get a vector numerics. If only one of these is a character, then we will hit the situation that we had yesterday. If we have C, 1, 2, and then A, or even if this was 3 as a character, then it will convert everything as a character. So it parses your CSV file, looks if there are NAs, okay? It's not going to use these ones to infer the type, but then it looks at all the values and then it decides is it a number or is it a character. And if we have strings as factors equals true, which is default value, then it converts all the strings to factors. Okay. Yes?
Yeah, I have a relevant question. Right? How can we replace, because sometimes we need to find a calculation, so we need to replace the NA with some arbitrary value. So
Yeah.
after we impute that value.
Okay, so I'm going to show you how you could do that, but imputation is a very difficult topic. Okay, so what I'm going to show here is what kind of R syntax you could use to do that. But certainly when you have data, you can't blindly replace the missing values by a number. So I'm going to create a vector. It would be the same with the data frame. So here it is, and so I can. The first thing I need to do is to identify where are my missing values to know what elements I need to change, and I can do this with a function called isNA, and that function will return a logical where I have element true when I indeed had a missing value originally. And so now I can use this to do the subsetting of X to point specifically to the elements that are missing. And then I can say, well, these elements I want, for example, to replace by 4. I know here I choose 4 because it's the 4th element. You could use 0 or... So if I do this, now I have replaced, the values in X that were missing, I replaced them with 0. But, so that's how you would do it with basic R syntax, using isNA to identify the elements, and then use that to do subsetting and replace with the value you want. If you do high throughput biology data analysis, you would typically not do these kind of things by hand, because you would use dedicated tools that implement well-defined imputation methods. And one imputation method might be replacing by 0, but that is only valid in some circumstances. So you would want to use possibly more sophisticated tools first to see if imputation by 0 or left-sensitive imputation, that's a type of left-sensitive imputation, makes sense. But the R syntax would be something like this.
Very basic question. When you use the word parsing, many contexts I get. What exactly does parsing mean? And how many meanings does it have?
I should be much more careful. So I think I used the word parsing when I said that the function read.csv is going to parse that text file. So it's going to read that text file, and then it's going to kind of analyze the elements in that text file to make sense out of them. So for example, as I said, it's going to check, so these are lines with commas, so it's going to split all the lines along the commas, and then it knows that all the third elements in these split lines will have to come in the same line, and so it's going to check, are these all numbers, for example. So parsing is the operation of kind of reading something and making sense out of it to return it in a structured way. So we're going to carry on with the analysis of data frames, and Tomorrow we'll move to statistical topics, but for the rest of today, we're going to focus on these data frames. We have seen vectors, we have seen data frames. There are other types of data structures in R, but these are probably the two most important ones. But we are going to learn about different techniques to analyze these data frames. And so, because this is a new chapter, I'm going to create a new script file, new R script, and I'm going to store it as S03, and I'm going to call this tidy.r. Tidy.r because we are going to use a set of tools that expect to have tidy data as input. Okay? And these tools do not come with R out of the box, but they come as modules to R. And these modules in R are called packages. And normally you have the packs that we're going to use, you have them already. They are already installed. And you can load one of these packages with the function library and then provide the name of the package. So let's see, package is not installed. Well, that's not a bad thing because we can then install it all together with the function install packages. So I try to load a package tidyverse, which is actually a meta package. And if it's not available, we need to install it, and we can do this with the function install packages. So if I run it, R will automatically check on package repositories if there is such a package called tidyverse, and if there is, R will download tidyverse and all its dependencies and automatically download and install them. So all the red text that we see here is downloading a package, and all the black text that we see here is installing the package on my computer. So if you run install the packages tidyverse, you will, or your installation of R will check whether tidyverse exists in these package repositories and automatically download tidyverse and all its dependencies and automatically install them. So install the packages is something that you do only once, and once it's done, you can now load the package with the function library. So install the packages is something that you do only once, and then every time you close and restart R, you would need to reload that package with the function library. Okay? Yes?
You know you're going to use a lot of libraries. Do you load them all at once, or do you just load them as you go?
If I know that I'm going to use 3 or 4 packages, I would put 4 calls to library at the very top of my script. And then if suddenly I realize, oh, I need a 5th one, then what I generally do is that I add this 5th call to library again at the very top, so that when I open the script, I see, oh, I'm going to need all these packages. But that's a convention because I find it easy to look at the script and immediately see the packages that I will need. The important point is that I will not be able to use any of the tools, and by tools I really mean functions, from the tidyverse package or associated packages if I haven't loaded before. So could you try or install the packages tidyverse and then load the tidyverse package? If there was a big problem, for example, you don't have an internet connection, let me know, and then I'll show you that we can actually load only three packages that will get us the job done. The tidyverse is kind of a meta package. By loading tidyverse, we install a couple of more packages, even though, strictly speaking, we only need 3 or 4 today. And so the kind of first, oh, sorry. There. And in the meantime, I'm going to do some drawings here. So this is a tidy data set, like a data frame. And so we are going to learn a set of new functions that will allow us to do 4 types of manipulation on this data frame, or on this data set. Actually, we'll not call it data frame. One is to subset a certain number or a set of variables, like we did with providing the index or the number after the column. Okay? We'll see a slightly different way of doing it. Another operation that we will do is to select a certain number of rows. Actually, let me already write the names here. Select. Okay? If we are interested in a certain number of variables, we are going to select these variables. If we are interested in a certain number of rows of interest, for example, let's say that we have here the variable 1, 1, 1, 2, 2, 3, 3. Let's imagine that we are interested in the rows that match 1 and has a value 2. That's something that we are going to call filter. So we select columns and we filter rows. We're also going to learn how to add new columns. Let me represent this. Adding new columns is called mutate. And then the last operation that we are going to study is the following. Again, let's imagine that we have one variable that is called 1, and I have 1, 2, 2, 3, 3. Very often what we want to do is to perform some calculations on only the observations that correspond to 1 is 1, 1 is 2, and 1 is 3. So we want to group this big data set into 3 smaller data sets based on the variable 1, and then we are going to want to repeat a certain calculation. Okay, so this is a group by, and then repeat a certain calculation on each of these subset of data. And eventually, when we have, let's say we calculate something x, so on is 2, we are going to want to combine these, or summarize some information in these subroutines. So what we're going to see are selections, filtering, mutate, and then grouping some observations into subgroups, and then calculate, summarize. Not going to light here. Either with an S or a Z. Or a Z, sorry. So these are the operations that we are going to see, and how are we going to do this? By using these functions in a package that is part of the type groups. So IPRG, and I'm going to read my data in as an IPRG, but this time, and I know it's confusing, and there are no good reasons for this to be confusing other than history. and different views of the world or how to name things. I'm going to use now a function called read_CSV to read my data, the same data that I read before. And now IPRG, it's the same data undelivered. Okay? It just happens that it's presented in a slightly different way. Okay? So the only difference is that we are going to use read_CSV. That function comes from a package of the tidyverse. So before calling a library tidyverse, read_CSV will not work. You will get an error saying that function not found. And I create a variable that I call IPRG again, and here it is. And it's the same data, but it's presented in a slightly different way. So this is called a tibble. It's a queued table because it's displayed in a queued way. We are not overwhelmed with all the information that is printed on screen. It tells us the table, 36,121 rows times 7. So these concepts that we learned are still correct. That many observations, that many variables, and then it prints only some of these variables, and then it tells us that, and some of these observations, that we have that many more rows and 2 more variables. And these variables are intensity and tag replicate. It also tells us that protein is a character, log2 intensity is a double, RON is a character, condition is a character, bioreplicate is a double, and so on. Yes?
Wouldn't you be calling, naming those tags vectors?
No, these are characters. CHR stands for characters. So, but that's a very good observation. Read_CSV does not do this conversion like read.csv does. Now, having said that, you could have used read.csv for all the rest of the visual, the manipulations that we are going to do. Yes?
Did I miss, did you type that fully, or did you just choose something and that file name automatically came
Huh?
into these cases? The file name,
Yes.
did you type in the whole name of the...
No, I cheated. But I have told you several times that I cheat. Look, data, and then tab, IP, tab. So tab completion is extremely useful. I appreciate that using the keyboard is at times a little bit annoying when we have lots of things to type. But that's why we use the tab key so often. Okay, so I have this IPRG variable, and it's like a data frame, but a queued version of data frame called a tibble. And so, for example, we had a discussion before with the rounding, and indeed that's what the tibble does automatically here with only one significant value. And here it also presents these intensities, these large numbers, as with a scientific notation. So the first operation that we are going to learn that I described there is select. So we want to select some columns. By definition, when we use select, it's variables columns. Well, we have to specify where from, that's IPRG. And for example, we want to select proteins, from and condition. So, protein, yeah, right. So I select from my IPRG data frame variables protein, ROM, condition. And somebody would, I assume most of you look at this and want to ask a question or make a comment. Yes?
Why is the protein passed as a variable and not like?
Yes, exactly, indeed. With this type of tools, we do not need to quote protein RON condition. It's handled like a variable. That also saves us some typing. So this is a variable. Well, actually, protein run and conditions are like variables inside IPRG. So that's the more technical explanation. But if we use these tools from the tidyverse, we generally don't need to quote, but we can write them as they are.
If we suppose we quote, would that create any problem?
I think it does. Let's try. Oh no, so it works. We can also quote them. But in general, when you use these kind of tools, and in other conditions, for example with the visualization, as we will see I think this afternoon, they should not be quoted. So in general, when you use these tools from the tidyverse, you don't need to quote, and you are not expected to quote the names of your variables. So we can select rows, but we can also filter, we can select columns. It's like the red and blue and green, right? You do the translation for me. We can also filter rows observations. Where from? Well, from IPRG. And for example, we could say that we want the bio replicate to be equal to 1. So the same as or equal as is 2 equal signs. Because 1 equal sign means assigning a value. It's a assignment operator. So in computer language, if we ask, is this equal to this? We need to have a double equal sign. And indeed, doing this will return the 9,079 observations that have bioreplicate equal to 1.
Hey, Laura?
Yes?
So your operation seems to be putting in those comments. The kibble.
This here?
Yeah.
Yes. So that's the default way how these tables are printed out, are shown. Here is the data with some additional comments if you want. These comments are part of the output. They don't show?
No.
Maybe it's a different version. Oh, but that's a data frame. What you're looking at. So could you execute line 3? Okay. Oh, data is on source. Now you execute it. Now you read your data as a table. Now it will display it. But it's a different display. The data is the same. Right. Now, just for your information, we could have done the same thing here with the other notation. And I'm going to type it for you. IPRG $bioreplicate equals 1. This creates a vector of logicals of length equal to the number of rows. And then I use this in IPRG to do the filtering along the rows. Okay, so this and that are equivalent. But now I'm going to show you something else that will make this very attractive. And what I'm going to show you now is a new cryptic character that you can automatically create. We can automatically create by pressing Control-Shift-M. It's this sign, percentage greater than percentage. And that's the pipe operator. So let me do the same thing that I did here on line 7 with the pipe operator. I say IPRG, and that IPRG is going to be piped into the next function. And the next function that I want to use is select. And what do I want to select? As before, 3 variables. Actually, I'm going to just to select 2 variables to save me some typing. Protein and ROM. But now I do not need to specify where from. Here, my first argument was IPRG. Now I do not need to specify this. The data frame that I'm going to use to do my selection is by default the one that is piped from the left-hand side. Okay. So this really means take the IPRG data and select protein and ROM. And I can run this and I get all my observations but only 2 columns. But when does this become really useful? You know, it's not, we haven't saved any typing from this, from this to that. But the piping allows us to chain more operations. So I'm going to put this on a new line to make it easier to read. I'm going to add here a new pipe operator, and now I'm going to say filter. I'm going to add BioC replicate, and I'm going to say I want to filter BioC equals 1.
BioC.
BioC. No, bioreplicates. Here, bioreplicate, not BioC. So what do I have here? I have a new table with 9,079 rows and 3 columns. So this table corresponds to the 3 columns that I selected here, but a subset of rows. So now these 3 lines of code correspond to, if you want, these 2, but they are chained one in another. Here I have a tidy data set that is passed as input to select. Select returns a tidy data set. Okay, here the tidy data set is returned and is piped automatically as input to filter, and then filter does its job. And we could have many more operations that are piped one to another. So writing the code like this makes it actually much more similar to the way we think, and we can construct manipulations, a set of operations. We kind of pipe the output from one operation as an input to the operation. And so the combination of these tidy tools like select, filter, and the piping makes it much easier to write code the way we think, rather than using this kind of syntax. But that's the default R syntax, so it's important to know it. But once you know it, it's good to move on to maybe more modern tools with a easier syntax to learn. And so that's what we're going to focus on until lunchtime.
Question. I was wondering if you could explain just line 14 through 16 one more time for me.
Yes, of course. So this operator means, okay, it's the arrow pointing like there. It means I take a tidy data set and then pass it to my next mate. Okay? So the first pipe operator gets, on one hand side, a tidy data. It's a table, and it passes to its next mate. The next mate is select. What does select do? Select selects columns. But on what? On the table, on the tidy data frame. But that's exactly what it gets from the pipe operator. So now I'm select, I get this tidy data set, I do my work, and then I return, that's the output of the function, but the output of the function is now passed to the pipe operator. So the pipe operator takes this new tidy data set, and we don't need to know how this data set looks like there. You know, that's our job, not ours, but ours job, to do the selecting, the filtering, right? We just type the command, so I have no idea how it looks like there. Assuming it worked, assuming I didn't type BioC replicate by bioreplicate, I know that I have a tidy data set there. So the pipe operator gets it and passes it to the next operation, which is filter. filter knows that it always operates off tidy data, and that's what gets passed by the pipe here, and that it does its job, which is filtering rows. And filter returns a tidy data set, and that tidy data set is returned and kind of stumbles on the R console and is displayed. Yes?
So for the filter function, that gives you what you're asking it for, not take out what you,
Yes.
right?
Yes.
So you ask for what you want, and that's the filter. So you
Yes.
give only what you want, not the.
And here I want BioC replicate equal to 1. I could also say BioC replicate different of 1, and then I would get all the other ones. But here I ask things that are different. Okay, so a little exercise for you. I'm going to type the exercise here. I want first intensities higher than 10 to the 8, and I only want variables, protein, condition, and intensity. So could you write a set of operations that will return proteins that are highly expressed, and I define here highly expressed by intensity, that there is a column called density, greater than 10 to the 8, and I only want to see these 3 variables using this notation. Yes, okay, so let's check that as an exercise together. So I start with IPRG, and then I use Shift Control M to write my pipe operator. And so what I'm going to do now, I'm going to start with a filter operation. And I want to filter on the intensity, and I want it to be greater than 8. And then I'm going to keep on piping, and then now select the columns of interest, and these would be protein, condition, and intensity. And so the question was this underlining here. This is just meant to make it easier to read, because we have 3 numbers that are not underlined, 3 that are underlined, and the next 2 that are not underlined. And it's supposed to help us to figure out that this is 117 million and blah, blah. So it's just a visual guide that is handled by, kind of on the fly when this is displayed. I don't know if it's possible to force this display to switch to scientific notation. I think if we type IPRG, here it switches to scientific notation because we have many variables, and so it's a little bit shorter, and it saves space. So this is something that is done, it's a kind of heuristic done by the package that handles the display of tables. I don't know if this can be parameterized. But the data, the underlying data, is always the same. Questions?
Is there a difference whether we go filtering first and selecting second, or vice versa?
Yeah. So here, let me run this again. I display the intensity, but I would arguably not be interested in displaying the intensity because I know that all these proteins have a high intensity, and that's what I'm interested in. So I could very well say I'm not displaying intensity because I know all these proteins satisfy my constraint or my requirement. But now let's try to do this, but put them the other way around. Run this. And now I get an error because here I say just keep protein and condition, and the intensity is not there anymore to do my filtering. So, yes. If I include intensity here, then it's going to work. But if I didn't want to see intensity, then again here we need to do a select protein condition. So in general, well, you have to make sure that the order of your operations can have different results. And typically, the selection of the columns is something that we would do at the very end, because that's only there to make it easier to look at. So that was for select and filter. The next one that I wrote there on the table is mutate. So IPRG, and what do I want to do with IPRG? Well, I want to mutate that data frame. And then, for example, if I want to have, actually, what are the names that I have? IPRG. So I have intensities and log10 intensities. Well, let's imagine that I want to create a new variable called log10 int, and that one should be computed by using the log10 value of intensity. So I can execute this. But actually, I have too many columns here. As you can see, log10 int appears here. So what I'm going to do is I'm going to pipe this in a select, for example, protein intensity and log10 int, just to make it easier to visualize. So now suddenly to change the output is only one piping and select. Okay, so, I think that's another nice way of piping operations. So here I say mutate. Mutate means create a new column, a new variable that I want to call log10 int. And how do I compute this? By using log10. Log10 is a function, and then intensity is the name of an existing variable. And that creates this new variable log10 int. I can now let me following. I'm going to select now. I'm going to first select to make it easier to visualize. So we can mutate one or multiple columns. I don't know, twice int equals 2 times intensity. And execute this. So I can have inside one call to mutate multiple operations to create multiple columns. So log10 intensity or twice the intensity. And before the call to mutate, there is no variable log10 int or twice int. But afterwards, of course, these variables exist. So now I could have filters, for example. Filters log10 int greater than 24 or something like that. Yes?
Just to clarify, but we just actually just making basically another column.
Yes. As shown there, mutate is to create a new variable, a new column. Yes.
Is there a way to remove columns?
Pardon?
Is there a way to remove columns?
Sorry.
Sorry, is there a way to remove?
Remove.
Yep.
So IPRG. Let's see, select minus what? Intensity. So we can still use the minus here to mean everything but the intensity.
Okay.
Yes.
So mutate rows only for columns, or for rows also? You want to add a new row?
Creating new rows. No, there is no default function for that. But that doesn't make much sense because your rows are your observations. So you don't create your observations unless you do simulations. But if your observations are real data.
So they have like a column space or something, right? So your observations are coming in.
Yes, but no. No. Here in this type of data analysis with tidy data, your observations are your rows and your variables
It's
are
not your column space.
No. That's the way the data is formatted. That's the tidy data concept. And all these functions are meant to be used on tidy data. And because they have some expectations. And that's why there is this kind of nice syntax that
Mutate
knows.
doesn't work for R.
This is for
Like the R, without the package, the library mutate won't work.
no, mutate only works if you load the tidyverse package. Yes. But it works on the data frame. It doesn't need to be a table, but it expects to have that kind of data structure. And that's why there is no function to create new rows, because these are observations, so you generally don't create new observations. But you do create new variables. So what we have seen so far in terms of reading data from this is read.csv or read_csv. Yes?
So the difference between a table and a data frame is just tidyverse terminology, or is there any other difference?
No, a table is a data frame, but that is displayed like this. Under the hood, it's still a data frame, but it has some bells and whistles, and it's displayed in a nice way, rather than too much information on the screen and we can't see it. But all these operations can be used with a data frame. But to be able to pipe these operations, the assumptions are that these are tidy tables, and they can be tidy tables or tidy data frames. You see? Yes?
I don't know why you would want to, but is there any way you could take a table and read or store that in a new data frame by itself, or a new object, I guess, by itself, so that you're not just seeing it? Because you're not interacting with it because it's a table, it's just a way of viewing a data frame, but the table itself you can.
So a table technically is a data frame, but it has this additional layer that allows it to be visualized. So you, let's see, as dot data frame, IPRG. So here we kind of say, no, I want it to behave like a data frame. But again, the data doesn't change. It's a different view that we have, but the data doesn't change. Does that answer your question?
Sort of, yeah.
No?
I'm just curious, like if you can, whatever operations are, when you're making the table, whatever operations are performed on it to compress it in this annotative way, can that itself become a new data structure that you I'm
So,
phrasing this correctly.
for example, here, these operations, and we get a table, but this table is only displayed. If it was a table that was interesting to me, I would store it into a new variable.
Okay, yeah.
And this variable happens to be a table because at the end of this operation, mutate returns a table. So these are still tables. They are displayed as tables, but they exist as tables. But this here, I should probably have clarified this. I only look at them and I don't store them. But of course, if this is a result of interest,
Yeah, I guess that's what I was trying to
then I would create a new variable, and it's a table because it was a table before, but it's a table that I select, I filter, I mutate, and it's still a table.
Okay. Thank you.
So data frame is not like something that is stored, and table is something that we look on the screen. No, absolutely not.
Yeah. Okay.
Sorry if that.
That clarifies that. Thank you.
So we have seen read.csv, okay, and we have seen read underscore CSV. And these functions can be used to read data that is stored on a hard drive as comma-separated values. But we can also store data as binary R objects. Because if we store it as CSV file, as text, there will be some simplifications that are done. Some conventions that are specific to the operating system that you use. There might be difference between Windows, Mac, or even if you have a Windows with an American configuration and Windows with a European configuration, where, for example, we use, instead of using dots, we use commas for decimals. Dates, goodness me, dates are horrible. Everybody encodes dates differently, and by that I don't only mean here in the States and in Europe, but different operating systems, even different versions of Excel encode dates differently. Right? So if we write this to a CSV file, what will happen, the way things are written to the CSV file will depend on the operating system we use. So for example, have you read that paper where they, well, you can test it yourself, there are gene names that suspiciously look like dates, like SAF1, OCT2. Well, if you read a table with SAF1, OCT2 in Excel, it will convert this to dates. And you can find these examples in published supplementary information where they have dates instead of these genes. Anyway, so CSV is useful if you have a data set in a spreadsheet, but if you have data that lives in R, there is no need to convert it to a CSV file to send it around. So it's these R objects, whether these are tables, vectors, data frames, they can be written to this immediately as R objects. And that guarantees that somebody else that has R, whatever the operating system, whatever the kind of local definition of the operating system, will be able to read them immediately. And these functions to save these objects are the function save. For example, data mytest.rda or rdata. Okay. So save is going to take a variable, in this case it's a table, and it's going to write it to this. Now here I would write it into the data directory because that's this directory, that's why I have it, to store data. And then, for example, I would like to call it mytest.rdata. Rdata is generally the extension that we use to store our data. Okay. If we have a file like that, we would not read it with read.csv or read_csv because it's not a CSV file. We would load it with the function load. For example, in your data directory, you have an iprgna file that we can load into R. So when we say load like this, it looks like nothing happens, but actually what has happened is that this new variable, iprgna, has been loaded automatically in my workspace. So there is a file, iprgna.rda, RDA or RData. Two extensions are commonly used. So load data, iprg data, will load the new variable iprgna, because that's how it was named, into your workspace. So what I would like you to do is, using this new, and we can have a look at it, iprgna. Okay, it's like the iprg data that we have. We have our 36,321 observations. We only have 6 columns: protein, run, condition, bioreplicate, intensity, tech, replicate. And what I would like you to do with this data set is to to calculate, like we did before, a log 10 intensity. Okay. But what let me type this here. So calculate log 10 intensity, but I would also like that you remove all proteins with missing values. So that will imply using filter and mutate. And a little help, we have seen this function, the function is.na. So for example, if I have a vector, I'm going to call it x here, 1, 2, 3, na. Which ones are na of x? This can be used to generate a vector of logicals, telling me which ones are na. Oh, and but one thing that we haven't seen is the negation operator, exclamation mark. So is na tells me which ones are missing. If I want to have those that are not missing, I say not. Not is na. And all the false are converted to true, and all the trues are converted to false. So with what we have seen so far, and the not is an A, you should be able to, starting from IPRG NA that has missing values, perform these two operations. So let me show you an example of is.na on our data set. So here I have shown the example is.na x, but we are not interested in x really. We are interested in IPRG NA dollar intensity. These are the data that have some missing values and that are annoying and that we would like to get rid of. So if I say is.na, from these 32,000 values, including some missing values, now I get 36,121 logicals saying true when that specific protein was missing and false when it was not. So what I'm interested in is not the proteins that have a missing value, but those that do not have a missing value. So if now I add a not sign, I get this vector that has true for all the proteins that have a quantitation value. So this is the vector that I want to use or tell filter to use to keep the proteins of interest. So it's this kind of construct that uses is not NA that I can use inside filter. Yes? So here I'm not using these tidy tools. Here I'm taking my data frame and I extract column intensity. So this is another notation for but it's shorter to time. So this demonstrates how to use is an A, or in this case is not an A, to construct a vector that can be reused by filter. If we have this, yes. Now it returns a new table or data frame, and each cell has a true or false depending whether it's not missing or it is missing. But we don't want to do filtering on the whole data frame. We want to target this this column. And so let's do that exercise together, because I really want to finish one thing before lunch at 12:30. So IPRG NA. So this is the data set that I want to use. And I asked you to load this data set because it has missing values here. So we could use this one directly to mutate log10 int equals log10, and inside here I use column names as variable names. And so I can do this, but unfortunately it's not displayed here. So let me So I get missing values at my log10 int. And so I want to get rid of these missing values. And by the way, I could do this before or after my mutate call, if I want to get rid of those that have missing values in intensity, or I could also get rid of those that have missing values in log10 intensity, because if I had the missing values here, I will also have it here. So let me proceed and do the filtering afterwards. So I want to filter, okay, because I want to subset my observations. And what's the variable I want to use to do the subsetting? Well, let's say intensity. The example we had before was filtering, where we said we only want intensities that are, for example, greater than 10 to the 8. But let's try to do this manually. IPRG, whether I use IPRG, NA or not, it doesn't matter, except for these missing values. Greater 1.8. This is what I get, right? This gives me a vector of logicals with true or false, depending on my condition. So I want to compute a vector of logicals inside my filter, but it is now I don't want to have high intensities. I want to have intensities that are not equal to NA. And how do we ask the question, is equal or is not equal to NA? In R, we use the is.NA function. And so far we have limited ourselves to chaining 2 or 3 operations, but this is something that you can keep on doing 4, 5, 6 operations depending on the questions you have. And the way you build these is really one by one. You run the first one, you look, does it make sense, the result that I have? Yes. Now I chain my second operation. Does it still work? Because if you write 4 or 5 operations and then you get an error, you'll anyway have to delete one by one to find where you have error. So it's more efficient to build one by one as long as things work. Yes?
Oh, never mind. I just got my question.
Okay. So we have seen select, we have seen filter, we have seen mutate, and have left the best for the end. It's group by and summarize. And that's really, really nice. It's very good. So let's keep on with IPRG. We could use IPRG-NA, but let's just get rid of the missing values for now. And let's first test the group by function. And let's say we want to group by conditions. So condition. Yes, here we go. So the example I had there was wrong, but it was the same with the condition. What do I get? So I still have a table with 36,321 observations and 7 variables, but this table has groups. It's grouped by variable condition, and I have 4 groups. That is the effect of saying group by condition. I could also say group by condition by the C bracket. Run this. Again, by the C. By the C comes from my Here we go. So now I have still 36,321 rows, 7 variables, but now I have my groupings based on condition and voice C replicate. And I still have 4 groups, because it happens that my condition and my voice C replicate match each other exactly. So group by, and I can have one or multiple, group by one or multiple conditions. So I'm going to remove voice C replicate here. That's needed. Okay. Only annotates this table, saying some observations belong to one condition, some other observations belong to the other conditions. However, what is interesting now is that all operations that are done will be done in parallel on the different subgroups. And so we can use the summarize function to perform a calculation and then summarize, group by these 4 pieces of information together. And the type of summaries that we have are calculating a metric, a new metric, that aggregates or summarizes all the information that we have within groups. So for example, I can calculate a new variable mean int that is the mean of intensity. And so if I run this, my output will be a new table, a tidy data. But this new table will only have 4 observations, 4 rows for my 4 conditions. And 2 variables, variable condition. I already had my variable condition before, but I had 32,000 observations with conditions. Now I only have 4 observations corresponding to these 4 groups and the mean intensity within each of these groups. So here's an exercise for you. Could you repeat that analysis, but change 2 things? Repeat on this data set, but calculate the median intensity by. Okay. So we use the function mean here. There is a function median. Repeat this calculation. Let me clear my screen and show it at the top. So not the mean intensity, but the median intensity. But please, you don't use IPRG, but use IPRG NA. Okay, let's do this exercise together. So IPRGNA is the data set that we want to use. And we want to calculate the median. So let me first do here group by condition. And then that would clearly be the first thing to do. Summarize that int equals median intensity. And we run this, and then we see that we get missing values everywhere. Okay? So that's how it works. It's not like I know the answer to the exercise. In reality, we try something and then realize, oh, it doesn't work. And then maybe we will say IPRG GNA, kind of look at it and see, oh, yes, okay, I have missing values. So how are we going to solve this? So I'm going to start by making a suggestion. Yes?
So the median function was not there outside of tidyverse. Tidyverse has a function for.
No, median, that's the plain normal median
It's a
function.
normal-
That
okay.
we,
I remember somebody else asking how we can find the median, and you said you subtract, like you go on the, you see the length of the vector and then go middle.
oh,
There's
that
a
was
function.
to find the middle row, and we used the median.
Right, but you could have done median.
Oh yeah, we could have taken median of 1 to 36,421. Yes, yes.
I thought.
No, so mean, median, log 10, these are plain R functions that are used as
Yeah.
part of the tidyverse, yes. So I'm going to keep this here and then say, well, what have we seen so far? We have seen that we can filter and say not is an A intensity. Okay. I rerun this, and I must not forget to type, and now I get median values for my four conditions. Okay. But there is another possibility where I don't do any filtering, but I add an A dot rm equals true to median. And now median is going to calculate, but first, before calculating that value, it's going to remove the medians, as we have seen yesterday with me. So I can either filter manually, remove the intensities that have an X, and then calculate my median, or my personal preferred option is to use median and then an A dot rm. And now, why do I prefer this one? And here's an exercise where I think a substantial fraction of my students did not find the right answer. It was not with proteomics. They are too young. They don't know about omics technologies. But the exercise, the data that we use are students that pass exams and they get marks. Microphone. It's time. It's time. Do you want to hear about my students now or later? Very quickly. So, they have exams. Exam 1, exam 2. Okay, each row is an observation as a student. And let's say student A was missing for the first exam, and then out of 10 had 7 out of 10 in the second exam. A, B, C, D. Student B had 6 and A, 6, 6, 5 and A. And let's say that these students belong to groups 1, 1, 2, 2. And I want to calculate the mean scores per exam per group. Okay. But so if I remove my filtering, where any of the exam has an A, I'm going to drop this completely, and these two lines completely, and this line completely. Whereas I would not want, if I want to calculate this average for the exam, I would only want to drop this value, but keep 6, 6, and 5. And if I want to calculate something for this exam, I would want to drop this and this value, but keep 7 and 6. And not drop the observations that have any value, any NA value in any exam. Okay? And so, in this case, it doesn't matter because we have only one column. But if we start filtering here with NAs and exams, this is the situation where we would have. That's why, although in this case it doesn't matter, I think this is kind of easier. There are no unexpected side effects. Okay? So that was it for the tidyverse, and these 4 functions: select, filter, mutate, summarize, extremely powerful. I mean, these are nice results, right? In 3 lines of code to calculate these. And we could have multiple groups: condition, technical replicates, and so on, and then the grouping would do all possible combinations. Okay, so that's it. Thank you very much. Sorry you're 6 minutes late again, but I'll see you back this afternoon.